Hi, welcome to the fifth lecture on connectedness. This is part of the topology series. In the last lecture, we talked about characterizing a space, connected space, by means of continuous function from the space to the discrete space plus or minus 1, where plus or minus 1 is considered as a subspace of R with the usual topology. And we also gave some applications. Today we are going to continue applications, but mostly in the context of R and Rn, etc. Okay, as I said, general topology set theory thing is okay, but if you want to go further, you should learn how to work with subsets of Euclidean spaces and something similar, which are more geometric, which also will require better understanding. Okay, so let us get started. Yeah, I hope everything is all right. Okay, so let us make first some observations before I go further. We say if space x tau x is connected if and only if every continuous function f from x to plus or minus 1 as a subset of R, which is same as saying f of x is contained in plus or minus 1, okay, is a constant. This is our characterization. Very simple characterization we did. The first thing we should notice is what all we require was this plus or minus 1 is a discrete space. Therefore, singleton 1 and singleton minus 1 are both open as well as closed. Okay. So if it's not a constant, then we get f inverse of the singleton set will be a non-empty set, a proper subset of x, and it is both open and closed. That will contradict connectedness. That's a basic argument. So if you go through this must be easy. So please go through it. So I will say x tau x is connected if and only if every continuous function f from x to a discrete space is a constant. Notice that if the discrete space has only one element, then it's of course it's a constant. So you do not assume the discrete space has more than one element. Suppose, let us call the discrete space as D. Okay, suppose D has more than two elements, well, not more than one element, at least two elements, right? Then you can argue the same way. Let's start with D1 and D2, D1 not equal to D2, right? So if X is connected and such an F, there is an F from X to D which is not a constant, that means there is at least f of x1 is not equal to f of x2. Call this as D1, call this as D2. Then f inverse of singleton, okay, this will be open and closed because singleton D1 is closed and open, and this is not empty because x1 belongs to this, and it's not equal to all of capital X because x2 is not here. You understand? So it's exactly the same logic. Please go through, convince yourself. So there is nothing, no sanctity about plus or minus 1. What all we require is a discrete space. So yeah, okay. Please understand this. This is equivalent theorem. So in particular, if I have a function f from x tau x to z as a subset of R, okay, x is connected if only if any such function must be a constant. Do you see that? Okay. Right. Now let's go through this. So we have proved in our first lecture or in the second lecture, this is a connected subset of R. Okay, any closed and bounded interval is a connected subset. Now you can ask what happens to open interval or intervals of the form AB or AB or open interval AB or the interval A infinity or the interval minus infinity to A and so on. Right? What do I know? Do you remember we already proved if a subset of R is not an interval, it is not connected. That we have proved. Now what we want to say is any interval that is of R is connected. We proved only this one, now we want to prove all such things. The proof is very easy. See, let us look at, for example, K to B. Now do you see that this is the union of A to B minus 1 upon N. Okay, there are certain subtle points. Okay, it will be nice to say this is good enough, all of you will agree. The first thing is why this union? This is by Archimedean property. Because you start with any x here, okay, notice that this is contained, each one of them is contained in AB. And why this equality holds? A, O, B. Yes. Now suppose, okay, therefore x is less than b, that means b minus x is positive. Therefore by Archimedean property I know n times b minus x, there is an n such that this is greater than 1. That means b minus x is greater than 1 by n. That means b is greater than x plus 1 by n. Or which is same as saying x is less than b minus 1 by n. Do you understand this? Therefore any x, given any x, there is an n so that x belongs to this interval. Okay, pause, review, proceed. Therefore, for every x in the interval AB, by Archimedean property, there exists n natural number so that x belongs to actually A to B minus 1 by n. In particular, A to B minus 1 by n closed. Okay? Right. Now, the next thing is observe that A belongs to each of the A minus B minus 1 by n. Now, it may happen B minus 1 by n may be strictly less than A. If n is very small, suppose this is my B, okay, A minus, if I take 1 by n, it may be less than A. Are you following? Suppose I take A and B equal to, let's say, A plus 1 by, okay, 10, right? Then B by half will be less than already there. You follow that? But remember again the definition of interval A, B, this is an interval for any real number A and B in R. The interval AB is set of all real numbers x so that x must be less than A and x must be greater than A and x must be less than or equal to B, greater than or equal to A. Right? So any x must satisfy two simultaneous conditions. Therefore, if I write something like 2 comma 1, okay, this interval is empty interval, empty set. Why? Because x must be greater than or equal to 2 but must be less than 1. Okay, these are the things you must not have learned, because whenever you think of an interval, you assume A is less than or equal to B. Okay, that's why various problems will come. Okay, or you may even assume A is strictly less than B. You don't have to assume. Okay. Simple. You may think these are all topology, but you know, many problems you are very uncomfortable with various things because you try to see the intuition and then you want to believe that. Okay, it's better to understand the basics very thoroughly. Okay, come back. Therefore, what I proved was A to B. This is a union of closed interval A, B minus 1 by n closed. This is n. And what happens? There is a possibility for certain n this may be empty set. Okay? No problem. Very good. Next, we know each of them is, this is closed and bounded, therefore these are all connected. This we had already seen. Right? Now I want to say this is connected. Right? So what do I have to do? I have to look for a continuous function suppose this is a continuous function which said that f of a b is contained in plus or minus 1. Then this is continuous. Then I have to prove f is a constant. Right? Okay. Let us do that. Now notice that when I restrict to give me any x in the interval a b, I am claiming fx is same as fu. Okay, this is our claim. Then does it prove f is a constant? Yes, because f is the constant equal to f of a. Right? Okay. How do I prove that? Given any x in a b, then I know this is the union of a b minus 1 by n. Right? Therefore, there exists an n such that x belong to a b minus 1 by n. Right? Now, when I restrict f to a b minus 1 by n, this is again a constant function. This is again a continuous function taking values such that plus or minus 1, where this is this set. Yeah? Right? Why? Now this is a continuous function. This is what we said, right? If f is from x to y continuous, if a is a subset of x, I restrict f to a, then f is continuous on a with subspace topology. Therefore, this is continuous. Now, what do I know about this? This is a connected set. Therefore, f is a constant. On where? On a to b minus 1 by n. Therefore, this constant for all x here, or for all every t here, f of t must be f of a. Right? And x belongs to this, therefore I prove this claim. So what do you think I have proved? I have proved any continuous function from, so any continuous function is a constant. This implies a, b is connected. Okay. This also follows from whatever we did. Okay. What I did was, if ua equal union ai, so that for all I and j, ai intersection aj is not empty, then and if these are connected, then a is connected. Now what are my ai? ai are an. an is a to b minus 1 by n. These are all connected, and an intersection am is not empty. In fact, little a will be an element of everything. So this also follows from earlier result. Okay. I just want to give a variety so that, in a typical classroom, because of the time constraint, the teacher will not be able to go through all these things. But they expect, if you want to master, you should go through it on your own. But you may not know, if you have not understood the basic concepts, you may not know what are the things I have to go through again and again. Are there different approaches? I am planning to use this. That's why the connectedness might have been done in less than 3 lectures, 2 lectures in a classroom. We are already in the 5th lecture. Yeah? You should appreciate, okay, the sincerity with which I am teaching. Yeah? Do you like it? Okay, good. Right. Now, how will you do the other one? I'm sure all of you know this will be union of a plus 1 by n to b. And how about this? This is the union of, what? A plus 1 by n closed and b minus 1 by n. Closed. Okay. And how about a infinity? This is union of a plus 1 by n. Yeah, and so on. So what is the final result we have proved? final grand result. A subset of R with usual topology, of course, is connected if and only if it is an interval. Have you proved it? Yes. How did you prove that? You prove that if a subset of R is not an interval, it's not connected, you prove. Conversely, if it's an interval, it's connected. Okay. So we have proved all the intervals. There is one small subtlety. Again, remember, empty set is an interval. As a subset of R is an interval. Why? If it is not, what you should give me? You have to give it 2 points x and y in empty set and a point z so that x less than z less than y with so that z is not in empty set. But you can't do this because empty set you cannot find 2 points. Therefore, since you cannot do that, are you following? This is why your logic should be good. If it's an interval, then for every element x and y in that set and every z between x and y, z must be in the set. So, if it's not an interval, I have to negate this sentence. If I negate the sentence, that means there exists 2 points x and y in that set and a point z in between x and y, and that point in between point does not lie in the set. That means if I want to prove if phi is not an interval, then I have to produce 2 elements in the empty set. I can't do that. Yeah. Please, if your logic is bad, please go through my foundation lectures, the first 1 or 2 lectures where I look at this kind of negation, quantifiers, etc. Please learn that. Okay. Refer to foundations if required. Okay. So empty set is always connected, and that's true for any subset also. X tau x, and if I consider empty set as this, then empty set is connected. Okay. Why? Again, use the same similar logic. Either our definition of connectedness. Okay, if it's not connected, there exists a subset A of empty set, so that A is not empty set and A is not equal to the full set, which is an empty set. Okay, do you understand? So you cannot find such a thing. If not, there is this, you can't do that. Therefore, by definition, it is connected. Okay, please pause, review, proceed. Okay, if you are not been very thorough with this kind of logical thinking, quantifiers, etc., my sincere request will be please watch my videos on those topics. Okay, because these are not taught. Okay, and that's why you find many times you have problem with the proofs. Okay, good. Right now, then I want to talk to you about something very interesting fact about connectedness, connected subsets of R, and intermediate theorem of real analysis. Okay, what is the relation between them? Let us go slow. Right? Suppose J is an interval. And I want to show J is connected. We had already shown that. Okay? Already proved. Okay? We just want to do it. So let us look at our connectedness characterization. What does it mean? Give me a continuous function from j, the interval, to r, so that f of j is contained in plus or minus 1. Then I have to prove f is a constant. Right? Now remember, this is a continuous function, right? And this is an interval. Therefore, by intermediate value theorem, I am assuming that all of you have gone through intermediate value theorem. Okay, there is a point. No, okay, let me give a proof. Suppose not. That means there exists x and y in z, so that f of x is plus 1 and f of y is minus 1. Because it's not constant, therefore it takes both the values, right? Very good. Now, by intermediate value theorem, there is a z between x and y. If x is less than y, x is less than z, less than y, or y less than z, less than x. So that f of z must be 0, because 0 is a value between minus 1 and 1. Therefore, there should exist a function z which is. Now, how do I know this? Remember, this z must lie in j. Why it should lie in j? Because j is an interval. This is the subtlety of the proof. Please understand. Since j is an interval, since x and y are given, okay, any point z, okay, between x and y must be an element of j. Therefore, f of z is defined. See, these are the subtleties at BSc you may not have learned very thoroughly. Okay, since it's an interval, so f of x is minus 1, f of y is 1. Okay, by intermediate value theorem, there is a z. You will simply say, where does it? The z lies between x and y. Very good. But I want to say f of z makes sense. How do I know that? Since x and y are in j is an interval, any point between x and y must also lie in j. Therefore, z also lies in j, and the domain of f is j. Therefore, f of z makes sense. Yeah, right. Therefore, f of z is 0. But that's a contradiction. Why it's a contradiction? Because f of j by assumption is contained in plus or minus 1 only. Okay, this contradiction shows, okay, the function f must be a constant. Okay, pause. Pause, review, proceed. Okay. Now, but topologists, okay, now let us say that in the topologist version is different. Now let us note that we already proved any interval, okay, we proved directly any interval j in R is connected. Right? Okay. Please go through that. Okay. Now I have proved this. Yeah. And the only connected subsets are intervals. Okay. These are the things we have already done. Right? Now let's look at. Now f is a continuous function from an interval j. Right? And let's assume this is a continuous function. Okay. Let us assume there exists x and y in j, so that f of x is alpha and f of y is beta. And let's assume alpha less than gamma less than beta. Then I want to prove there exists z in J so that f of z is gamma. This is your intermediate value theorem, right? So please understand, last time what we did was we assumed intermediate value theorem we know from real analysis and used it along with the characterization of connectedness by means of continuous functions that any interval is connected. Do you understand that? Please understand, that's what we proved. Now I want to turn the plate on. It's the other way around. What I want to prove? I want to say, assume I know what are all the connected subsets of R, and any interval in R is connected. The only connected subsets of R is intervals. I have proved it. I gave a direct proof, right? I proved closed interval A, B is connected, and from that I deduce any interval is connected. Okay, that is done. Now using this, I want to prove intermediate value theorem. Therefore, what does it follow? In some sense, it follows, okay, in a very vague sense, connectedness of an interval is equivalent to intermediate value theorem. Because assume connectedness of an interval, I proved intermediate value theorem. I am going to prove. And assume intermediate value theorem, I proved the connectedness of any interval. Do you see that? Okay, don't get confused. These are the things someone teachers don't want to explain in detail for the fear that this kind of technical things will kind of frighten students. But good students will thrive on such things. They will become more enthusiastic about the subject. Let us do that. Now, what do I know? So, let us assume my x is less than y with a Russell generality. Right? Now, since x and y belong to J, therefore the entire interval xy is contained in J. Do you agree with that? Yes? Yeah? Because give me any z in the interval, then x is less than z, less than y, but x and y are in J, therefore z is in J. That's the definition of interval. Right? Okay, good. Now restrict f to xy. Therefore, this is a function from xy to r. This is continuous, right? Restriction of any continuous function is continuous. Very good. Now, what do I know? F of x is alpha, f of y is beta, and alpha less than gamma less than beta. Alright? Now, since this is continuous, we had already seen the continuous image of a connected set, that is the image of a connected space under a continuous map is connected, right? So since we know this interval is connected, this is all we needed, right? We know the interval is connected. That's the first thing we proved using LU property, right? This is connected, therefore f of xy is a subset of R is connected. Is that clear? Very good. Now, what do I know? Okay, f of x, which is alpha, is less than gamma, is less than f of y, which is beta. Now, since this is connected, I know this is an interval. Therefore, f of xy, because we know we are characterized. What is our assumption? We know the only connected subsets of R are intervals, right? Therefore, this is an interval. Therefore, this is connected. Therefore, it's an interval. Okay, it's an interval. And now alpha and beta are in this interval, and alpha less than gamma less than beta. By the definition of interval, this implies gamma must be in f of xy. What does it mean to say gamma is there? This means it must be the image of a point in the interval xy under f. Therefore, there is a z in the interval AB such that gamma is f of z. Right? And gamma cannot be alpha and cannot be beta, because sorry, not gamma, that is given. What I mean is z cannot be in the interval xy, sorry. Therefore z, I say that it lies in the open interval xy. Why? If z is equal to x, then f of z, which is gamma, equal to f of x, which is alpha, a contradiction. Similarly, other way around. You follow that? That's it. So we have proved. Let me just summarize. Don't get confused. So the first thing, what I assumed was let me assume intermediate value theorem. Then I am going to prove any interval is connected subset of R. Okay? You understood? In the second case, what I assume is, I assume that I know any closed and bounded interval in R is connected. Okay? Then I want to derive the intermediate value theorem. You follow that? So I proved both the things. So please go through it. In the next lecture, we will look at some subsets of R and for n greater than or equal to 2. I hope you enjoyed this lecture. These things are very quickly passed through in typical lectures, course and classroom. Okay, please go through it, and if your basics are correct, you can see that again and again I emphasize why you have to learn the basics thoroughly, because many of you I know may not have learned basic real analysis. Okay, you may not even have learned what is the correct definition of interval, and there is something about continuity. You jump into that just because you want to learn connectedness. Okay, without proper background, you try to learn and you try to think, as I am going to be a savior. I am not a savior. Okay, you have to learn those things, the basics thoroughly. Then you will enjoy the lectures. You will also see, you will become confident. Okay, I hope all of you enjoy the lecture. We will meet again.